So we want to just make this point a bit clearer by introducing other loops and show what the difference between the self-inductance is and other kinds of inductance, just to make sure we understand what we're dealing with. So you have here loop 1 with a current I1, you have loop 2 with a current I2, loop 3 with a current I3. You could have many loops in space. And we want to get the magnetic field through loop 1, at some point through loop 1. So this B. And we know from the principle of superposition that the magnetic field at any point is the sum of the magnetic fields due to each source. So you have magnetic field B1 due to the current I1. B2 is the magnetic field here, but due to I2. And B3 is the magnetic field here, but due to loop 3. Now, if you get the magnetic flux through loop 1, then this magnetic flux has several components. You have magnetic flux through loop 1, but due to the magnetic field, due to the current in loop 1, and you have magnetic flux through loop 1, but due to the magnetic field due to current I2, and you have magnetic flux through loop 1 due to the magnetic field due to the current in I3. So you have different phi's here. And just to be very specific, what the self-inductance is, it's the magnetic flux in loop 1 due to the magnetic field or the current in loop 1 divided by the current I1. This is very specifically what the self-inductance is. And the reason why I put it here with other loops is because you can define other kinds of inductance called mutual inductance. For instance, you can take the magnetic flux through loop 1, but due to the current in loop 2, and divide that by I2, and you can call that a mutual inductance. Now, we're not going to study the mutual inductance in this course. It's available in the book, but we're not going to cover it in the course. So that's why I just want to mention what we're not going to cover and what we're going to cover, so you don't get confused if you get other problems later on. So then, as we said, self-inductance in loop 1 is defined as the magnetic flux through loop 1 due to the current in loop 1 divided by I1. And we said before, it depends only on the geometry. That means the magnetic flux is L times I1. Now the induced EMF is minus d phi by dt. We only have one loop here. So minus, there's no n here. There's no number of loops. It's only one loop. So minus d phi by dt. And if you plug in the phi, you get minus L di by dt. So this is the relationship to get the self-induced EMF. Now, what happens if this circuit has many loops, n loops? Then we'll define the self-inductance to be n times phi 11 over I1, where phi 11 is the magnetic flux through a single loop. And so this is then the definition of the self-inductance if your circuit has n loops. And again, L1 depends only on the geometry. And then phi 11 is equal to this quantity by cross multiplication. And now if you want to get the induced EMF in the circuit 1, it's minus n d phi by dt. You have the n because you have n loops. But when you multiply the n and you have phi, it has 1 over n, then the n's will cancel. And so you get again the same relationship that the induced EMF in circuit 1 is minus L1 di by dt. So this is again the relationship when you have n loops.